Let us start by reviewing what we are going to have for the final examination. And let's see what support we are preparing ourselves for the final examination. The midterm examination we are going to have on the February the 3rd, I think, and it's supposed to be the online. Anyway, I myself proposed the university to have the hybrid examination by open books, open everything, even though you come to the class. This term, we have the open stuff examination. And if that happen, just beware about the correctness of your work, because when we open book, Ajahn will very scrutinize, deep investigation on your problem solving skill. Anyway, the first problem on the final examination will include chapter 6, chapter 7, and chapter 8 at the same time. Actually, it's not just chapter 6, 7, 8. It go back to the chapter 1. The first one will include everything, but most of the time, the equation that we will use will come from chapter 1, chapter 6, and chapter 7. Let me put the writing pen for putting the mouse to write down over here, because if I write over there, your friend will not see it. Important equation that's going to involve in this. No, there is something wrong. Oh yeah, the equal red. Okay, we will have the equation sigma equal to force over A. That's going to start by the chapter 1. Okay, and also we will have the chapter 6. That's going to have the equation of sigma equal to my over I, the moment, times the distance y, and divided by moment of inertia. We will be talking about this later. And the other one, the chapter 7, gonna be talking about the transverse shear, how equal to VQ divided by the IT. I will be talking about the equation later. But what I need to tell you is the knowledge and skill from the engineering statistics, in which you guys are supposed to go back and review them. First, draw the free body diagram of the structure, including beam, including frame, including the sheet. And then you got to use the equation of equilibrium to determine the reaction. Okay, and not enough. You need to find the internal force. You need to find the internal moment. You also need to determine the internal shear. That means you got to cut the structure to draw the free body diagram of the segment of the structure, and then you determine the internal force, internal moment. And later, they're going to ask you to determine the stress. And then you combine this kind of stress together. That is going to be the chapter 8. And they ask you to draw what's so-called the stress element. What is the stress element? Stress element is a small piece of your structure that is going to be like usually is the square small section, and then they will define this stress as sigma x, because this one is the x direction, and this one as the sigma y direction, and also the shear stress. The shear stress, when it comes in four sides of the element. Okay, and then you go further to chapter 9 from the test. from the test. I will show you later. The force will fail, will make the structure fail, maybe just in the, for example, if you have the beam like this, and then you put the force here, the failure of the reinforced concrete beam may be cracked here. That is due to the moment. And sometimes it have the crack in this direction. That means it didn't crack only the moment. It's cracked by the moment and combined with the shear. And the direction of crack is not in the XY direction. It's in the inclined direction. That means you got to rotate this one to some of the other direction, X palm. And if rotate this by the angle of theta, okay, you can determine for a given angle, you can determine another stress. That's so-called, this is cannot adjust anyway. That's so-called the stress sigma sub x palm, and this one gonna be sigma sub y palm, and the also one you will see the tau sub x palm y palm. What it means is when you rotate the element, the value of the original stress change, and sometimes it change with the maximum normal stress we call principal stresses, and with some specific angle it will provide the maximum in plane shear. What I'm going to tell is, if you get sigma sub x, let's say 10, sigma sub y 10, tau sub x y 10, if you rotate for some angle, the value of sigma x palm can be 15. The value of sigma sub y palm may be 5. The value of tau sub x palm y palm may be 8. It's changed with angle. Okay. And for some specific angle, it will provide the maximum normal stress. Okay. It will provide the maximum in plane stress. And that's maximum normal stress, maximum in plane stress cause the crack of the structure. Okay, that's it, problem number 2. And then here we come to the problem number 3. The problem number 3, we come to design the beam. And again, this time, the shear diagram and the moment diagram will be very important. Okay, go back to the engine static. You may pass the engine static, but you may not pass the drawing of shear diagram, moment diagram. And I warn you, for the CE student, for the ME student, you're going to draw a lot of shear diagram and moment diagram in the near coming future. Okay, so go back and again review the engine static. And for the design, you know, we are going to determine M max from the moment diagram. We are going to determine the V max from the shear diagram, and then we determine the cross section of the beam based on the moment max, based on the V max. So this time we will get a section of the structure. Okay, and then later the beam under the force it will defect. For example, if you have the beam like this, is subjected to the force like this, it will have changing the shape like this. If there is the wall under the beam, the defected shape will compress the wall, and many times the wall can be cracked. So we need to prevent it by determining what's so-called the maximum deflection. And this maximum deflection will be set less than L over 240 if there is no wall under the beam, no wall. If there is a wall under the beam, the maximum deflection will be less. You got to divide the span L by 360. Okay, that is going to be the problem number 4. And then problem number 5, come to the column. And you can see for the short column, you can press it until it gets the yielding. But for the long column, the behavior different. The long column, when you compress it, it will deform like this. The column that deform like this, we call it buckling. Okay, the final one, we're going to determine the load that caused the buckling of the column. We call it critical load. And then we can determine the critical stress that's produced this one to be something like this. And the specific thing is when you release the force, it's go back at the original shape. Okay, this means the stress that occur here is going to be less than the sigma sub y. Okay, let's see. For the example, we come to the chapter 1. We have the structure like this. Okay, for the example, they're going to ask you to determine the reaction. They ask you to determine the normal force, shear force, and bending moment. And they give you some equation over here. Okay, and that's what I did show you before. This is for the chapter 1. Okay, this is for the chapter 7, and this one is going to be for the chapter 6, and you will determine this one for the equation here, this one for the equation here, and this one for the equation here. And if you determine them, the N and V and M wrong, that means what? The stresses you are looking for is going to be wrong. Okay, that is for the problem in 2 dimensions. In 3 dimensions, usually it's going to have the structure in the shape something like this. For the 3 dimensions, it's going to be asking you to determine the force in this section. Okay, that means you got to cut the top portion, and then you will determine the force occur here going to be N. Okay, so this one is going to be the moment M, and again if there is like a force here, you're going to determine the shear here. The same thing, whether it is in 2 dimensions or it is in 3 dimensions, you got to determine N, you got to determine V, you got to determine M to use it later to find the stresses. Okay, and what we have here is what the final product of the chapter 1 is going to be this one. This one we call is as before called the stress element. This called the stress element, but Ajahn will separate the problem 1 and problem 2. If we include them together, you make the problem wrong, problem 2 will be wrong too also. Okay, we will separate them. Ajahn will giving this one to you, and when Ajahn giving this one to you, this means this is going to be sigma x. Okay, this is going to be sigma y, and this is going to be tau sub x y. And then Ajahn will ask you if we rotate this one to some specific angle, like this theta, and we will get a new, sorry, I got to erase this first. I cannot erase it. Okay, that is something I got to install the driver later. We are going to determine this one for the sigma sub x palm, this one for the sigma sub y palm, and also we will determine later tau sub x palm y palm. Okay, and for this some specific angle, we will get the principal stress, and for some specific angle, we will get maximum in plane shear. That is teaching. In the second problem, 1 give you the theta, you determine sigma sub x palm, sigma sub y palm, tau sub x palm y palm. Okay. The second one, we are asking you to determine the maximum normal stress. That's called the principal stress, and their angles. The third, we are asking you to determine the tau max. Okay, and SOCS, normal stress with the ankle, that is eating. You may read later in your problem statement. And it's going to be problem number 2. And move to this one. For the problem number 3, we will give you the beam. The first thing you got to draw the what's so called the shear diagram and the moment diagram, and you are looking for Vmax and you are looking for Mmax. And again, when you draw it, there is 2 ways to draw it. One draw by the equation, another one draw by the so-called graphical method. I recommend you to use this. By using the graphical method, there is 6 relationships. The third 3 is going to involve with the drawing of the shear diagram. And let me recall you, it's going to be dV by dx equal to minus of the uniformly distributed load. Okay, that means what? Between this first portion, the slope gonna be 0. For the second portion, the slope is equal to minus of the loading W. Okay, and then the second one, we will write dV equal to minus W dx, and then you do the integration from A to B. Integration from A to B, you got V sub B minus V sub A. What is mean? The change of the shear from the B to the A equal to what? Equal to minus of the integration here is what? Is the area of W between A to B. Okay, it's the area between them, between A and B. The difference of the shear between B and A equal to the minus of the area of W. And then the third, if you have the upload P, the change of V is positive. If you have the downward P, the change of V is negative. Okay, we will be talking about this later. That is for the shear. Coming for the moment diagram, you also have one is the dm by dx equal to shear. The second one, you have dm equal to v dx, and you do the integration from the A to B, integration from the A to B, you got m sub b minus m sub a equal to the integration, the area of what? Of V diagram between A to B. Okay, and the third one that you are going to use is going to be the third one. If you have this kind of moment counterclockwise, okay, the delta M is going to be negative. If you have the clockwise moment, the delta M is going to be plus. If you do this correct, it's going to be a good start for the third problem. If you do it wrong, you end your calculation here. And usually the design of beam will have about 10 to 15 points. Okay, they are asking you for this. And then after you finish this, you use the maximum shear force, you use the maximum bending moment, and then you determine the section modulus that's going to tell you what type of section you are going to use. Okay, this kind of problem already, no, not yet, not show yet, is in the, I think the PowerPoint, I just put it in the live group, this morning. Go to the live group, This portion of the PowerPoint, go to the live group and open the file for the chapter 6. Go to 5822111. It's going to have There is no detail of this. Let me check. Anyway, I will report it later. Hey, sorry, I put the wrong file. And anyway, I will put them back later. Okay. And anyway, all of this is going to be your extra example later. Okay. And if you, when you find the section modulus, you got the section. And then later I will ask you to determine the maximum deflection and then compare it between L over 240 if there is no wall under the beam, and if there is the wall under the beam is going to be L over 360. Okay. Anyway, I record this. You will see that later. And the last one, the problem number 5, they're going to ask you to determine the bucking load of the column. Okay, both in the x-axis and y-axis. That's the main point. That is for the final examination, and we prepare for this. We're going to have chapter 6, chapter 7, chapter 8, chapter 9. No, chapter 10. Chapter 10 will be in the advanced mechanics of material. Yeah, chapter 11, chapter 12, chapter 13. That's total of 7 chapters within only 6 weeks. Okay, that's going to be the fast of the fastest. Okay, and then I should start our lecture now to let you guys to appreciate what we are going to have. Before we go further, go back to the 5 chapter that we are going to have before the examination, and we start by studying the two force members. It's going to subject to what? Tension, or if in some case it will be subjected to compression. Okay, and the equation to determine them is going to be the same equation. Okay, if you cut this one over here, if it's under compression, this guy will cause the normal stress, and the normal stress here by sigma equal to P over A. And then whatsoever, when you cool this one in tension, this one going to get elongation. Okay, and if you determine by divide the elongation by the original length, you got this one for the straight. And then for most of our engineering structure, the behavior of the structure will only in this portion in the linear elastic. During the linear elastic, Hooke's law applies, in which sigma equal to E epsilon. Okay, that is going to be in chapter 3. This is in chapter 1. This is in chapter 2. This is in chapter 3. And then you put this one, P over A equal to E delta over L, and then you get another equation. This one for chapter 4, right? You use this one in the chapter 4. And this one for the elongation when the structure is in linear elastic. If I like to determine the elongation in the plastic region, how can we do? How can we do? Just go to the stress strain diagram, and then the stress is going to be very high, and then you do the leading of the plastic strain from the diagram. And when you get the plastic strain from the diagram, the equation here going to be the strain at the plastic times L. This is the equation if the behavior of structure is in plastic rigid. Okay, now you guys are supposed to be very good on this already, right? You already finished reading your midterm examination, right? And then we come to the shear. And he said the shear can be separated into single shear and double shear. For the single shear, it's very easy. Just do something like this. We pull together. There is one cut, right? The force that I pull you going to be the shear force here. And for somehow we have this kind of connection. Two of your hands is put in my hand, and what we have is double shear because we're going to cut this portion and also this portion. They are double cut. So this one shear is going to be half of my force. Okay, so the we gonna check it depends on is single shear or double shear. Okay, it's going to be single shear. We going to be my force. If it's double shear, we going to be half of my force. Ajahn, how about single shear? Single shear, double shear is enough already. The single shear, let you do it later in the future. Okay, and then we have the other shear. That is the shear due to the torsion. And I would like to say it again, for the torsion is occur in the shaft that's connected to the engine or connected to the electrical motor. Okay, it's going to transmit the moment around the axis of the shaft. We call the moment around the axis of the shaft as the torsion. It's different. This is tension. Okay, this tension. This is torsion. You hear? If you have your girlfriend sometimes she pull you hear? That is going to be in tension. Okay, that's going to take you to somewhere with her. And sometimes she twists your ear. You see, yeah, this time she angry with you, not like to take you to somewhere. Okay, that's it for the chapter 5. That's it for the chapter 5. You have the torsion in chapter 5. And then the tau also has the shear stress strain diagram. Okay, and the shear stress strain diagram have something the shape like this. And again, the first portion of this is linear elastic. And then we have the relationship of tau equal to G gamma. This is called the shear modulus of elasticity. This called only the modulus of elasticity. Most of them determined by the slope, okay, in the linear portion. And then we have this equation to determine the angle of twist, okay, and we use this equation to determine the indeterminate structure also. Okay, that's finished for what we are going to have on the February the 3rd. Okay, if the examination is open book, you have for that. Put everything in the book. Yeah, and you will see that you cannot find. You will have no time to find what you put everything in the book. Okay. Ajahn Anop always have open book for his reinforced concrete design and also his tested concrete design. The problem is the time is limited, and you cannot looking for everything in the book. You cannot, because you have only limited time. So don't forget to remember something. Okay, that is the basic thing. And you may not remember everything, just some of them you may find them in the book. That's going to reduce your time of looking for the information. Okay, and then come to the 6th, the blue one. The equation is going to be this one. This one come from what? This one very easy. The ruler. Bend it. Okay. When you bend things, you use the moment to bend it. Okay. That means what? The start of this. You have your beam, something like this. And then you put the moment into it. The shape of this gonna be change. Okay. When the shape change like this, this is going to be in compression, right? And this is going to be in tension. If this one is the reinforced concrete, and you know that concrete cannot take the tension when the beam is in positive moment, you got to put the reinforcement on the bottom side of the beam. However, if the beam is subjected to the negative moment, this for negative moment, this one gonna be in tension, this one gonna be in compression, this is positive moment, okay, tension is here, this is negative moment, this is in tension, they are opposite, and this one you are going to put the reinforcement over here, okay, so this is important thing when you further study the reinforced concrete, okay, you got to know the way to put the reinforcement to the concrete beam to make it more strong or stronger, okay, and then later not only this one cause the concrete, you also has the transverse shear under the application of the force like this. The shear will cause the crack like this. Okay, the moment will cause the crack like this. So for the moment you put the reinforcement here, okay, to help the structure resist the crack. How about the inclined crack like that? What you are going to do? You're gonna put the stirrup. The stirrup is the steel in the vertical direction. So for the reinforcement to resist the shear, we put the stirrup over here to prevent the crack like this. Also, you got to put on both sides, okay, to prevent the crack. Okay, this is a small example. We are going to use the chapter 6 and chapter 7. For the chapter 6, this is the moment. This is I. I is what? I is moment of in shear. And then very simple one for the beam, we have this section. If this one is B, this one is H. The moment of inertia, you're going to talk about what's so-called the centroid, okay? And I said this one in compression, this one in tension, okay? This one in tension, this one in compression. So the beam usually will have the stress if the moment is positive. This one gonna be in compression. This one gonna be in tension. How about in between? If you said this is negative compression, if this is positive in tension, so what in between? It's going to have zero stress. Okay. In this case, the distribution of the stress will be compression in the top portion and going to be in tension in the bottom portion, and this point passing to the centroid, we call it neutral axis. That is, the axis have no stress, okay, and then you will see the effect of y is here. If you put this one is 0 and you put up is y, if y increase, the stress also increase, okay, it's increased by the linear of torsion. This torsion is in triangular shape. Okay, and the last one, moment of inertia over here is going to be VH cube divided by 12. And since the beam may have this kind of section, maybe I, maybe T, okay, maybe L, maybe C, I recommend you guys to review two more things. One, this means the centroid. Okay, that's from chapter 6 of the static. And another one, this means the moment of inertia. Okay, now that is chapter 9 for the centroid and chapter 10 for the moment of inertia. Go back and review them. If you find M is correct, if you find Y is correct, okay, but you do the wrong calculation for the I, your stress also be wrong. Okay, that is why I said you pass what the grade you pass for the static. If you pass static by A, you are good. Okay, if you pass the static by C, and I'm going to ask you which portion of static that you get the grade of C. Okay, if you get the grade of C by the shear diagram, by the centroid, by the moment of the shear, you are in good shape. But if you get a good grade from the static, from the friction, you are going to be in some problem to go back and review it. Okay, I asking you for that because this is very important. And then you come back to determine the tau equal to V. Okay, and also the I, and the T is very easy. T is the width of the section. The problem is the Q. I will be talking about the Q later. The Q is the moment of the area under the point that you find the tau about the notional axis. That is very long definition. Anyway, when you see what I show you, that's going to help. Okay. Okay. That's what we're going to study, the pink and the light green equation. And then this is chapter 6. Okay, we are going to go back and tying to draw the shear diagram and moment diagram. Before we can find this, we got to draw the free body diagram. We got to use the equation of equilibrium to determine the reaction. Okay, to determine the internal forces as moment. And next, I did explain to you already about the deformation of the beam, in which I put it over here. Okay, and I also talking about the importance of understanding the deformation of the beam. And later, we got the equation sigma equal to my over I. We're going to use this equation to analyze and design the beam, sometimes also the frame and the composite beam. And this is going to be one of our subject here. And let me move this one a little bit to one more chapter. That is going to be the chapter 7. In the chapter 7, again, we start by understanding the deformation of the beam and also use the equation. The equation that we are going to use is what? It's going to be tau equal to VQ over IT. We will use this equation again to analyze and design the beam and the frame and the composite beam later. Okay, And then chapter 8 is going to put the equation from chapter 1 combined with the chapter 6, combined with the chapter 7. And I will show you in this lecture. We will work together on this problem. Okay, let me talking a little bit about the equation, and after finish, we will have a break, and we will do this problem together. Okay, let me go back to the fractional equation on the chapter 6. On this one, I asked you again on chapter 6, chapter 7, chapter 8. Go back, review the shear diagram, moment diagram, determine the centroid, how to determine the moment of inertia. And when you bending, this is bent by the positive moment. Okay, the top is going to be in compression. This is going to be in compression. The bottom is going to be in tension. If you bring the rubber beam and you bend it, you will see on the top of this portion going to be contraction. Okay, that is mean it's going to be in compression, and the bottom going to be elongation. That is show us is in tension, and in between it has no contraction and no elongation. We call this one neutral, neutral. And the axis that pass to this neutral, we call neutral axis. And Ajahn will write N dot A dot later. That's show the axis of no stresses. And then when we do the consideration, that means the top is going to be in contraction, the bottom is going to be in tension, and what we have is the distribution of the strain on the beam going to be like that, and the stress on contraction going to be on this one is in compression. The bottom, this one going to be in tension. Okay, and I should ask you the effect of the Y. If Y is large, the deformation going to be large, and the stress going to be maximum. Okay, it's depending on the Y. Ajahn, what happened? Okay, let me show you this section first. On this section, you can see that due to the symmetry, due to the double symmetry of the section, if you measure up here and measure up here, if this one is 100 millimeter, you will find this one 50 millimeter, this one 50 millimeter. The maximum normal stress on the top and on the bottom going to be equal. Okay. However, if your section just be something like the T section, like this, and you will find the axis that's passing through the centroid like this. If you measure this one may be 40 millimeter. If you measure like this one gonna be 60 millimeter. So this time the normal stress gonna be maximum in this portion of the beam. So that is the effect of the Y. Okay, it's up to the section. If the section double symmetry, measure up and measure down, they are the same. Okay, maximum stress gonna be the same. If the section is a type of the T is a type of the C, measure up will be less than measure down. So the maximum stress for the positive moment gonna occur at the bottom. Okay, and let's see, this one will provide the stress distribution, something like this. But this one, we will have small at the top and large at the bottom. And what you may see, let me see, most of the time, we didn't much draw the stress distribution in this size. Most of the time, we draw it in this size. Okay, let me propose you to practice for the stress distribution on the right hand side. What I'm saying is, usually we have the beam like this, okay? And then when we cut this one, most of the time we will draw the free body diagram in this size, and the stress distribution also we usually draw in this size. And from the equation, I suggest you about it. Don't worry about the sign in front of this equation, but understand this one. This is for the positive moment. Okay, top is compression, the bottom is in tension. This one is the reverse, negative moment. Okay, remember this. Don't remember the sign, because the sign will make you confused later. Okay, understand the physical meaning. And then this moment here, and then I should say, for the moment, if you cut like this called the positive moment. Okay, this also, guys, okay. I would like to say, okay, and then the y, the effect of the y is already discussed. Okay, depending on the section. And then the I is the moment of inertia. It's dependent on is the square, is the rectangular, is the T, is the L section. Okay, depending on you. Okay, and maximum is here. I discussed this already. Okay, and then the type of the problem. First one is the analysis. In the analysis, Ajahn will provide you the dimension. Okay, you will know the 60, something like this, and they just ask you to determine the stress. It will not come easy like that. It will come something like this. Okay, I will discuss that later. That is called the analysis. And the analysis also can be separated into two parts. One is the analysis to determine the stress. Another one is the analysis to determine the force that can apply to the structure. Remember? And you also will have that in the examination. Number one. And this one, usually we don't care about that. The analysis will be something like this most of the time. And the second one, you do the design. To do the design, we are looking for the size of the section. Okay, that is another thing. This provides the size to determine the stress. Okay, this one provide you the allowable stress, and then asking you to determine the size is the opposite. You understand that, right? They are in the opposite direction. Analysis give you the dimension, determine the stress. Okay, the design give you the allowable stress to determine the
side. Okay, and I will finish this one over here, and let me talking a little bit more about chapter 7, and we will do some. Okay, on the chapter 7, we come to this portion, and then I show you here. I show you this picture. Let's see this picture. This is your senior 10 years ago. He cast the real reinforced concrete beam, and they put it into the frame. You can see the frame in the F4 building, and they put the force into the beam, and then they found the track. This kind of track is the track due to the bending moment. Okay, is usually occur in the middle portion of the beam. Why? Because at the middle portion of the beam, most of the time the moment is made. Okay, let's see if you put this structure by the force something like this. Okay, the reaction gonna be half, right? And the shear diagram of this gonna be up, constant, down, and then down, constant, up. This is a shear diagram. And the moment diagram of this gonna be this one, constant, and this one. The maximum moment is here. That is in between this portion. Okay, you can see a lot of crack due to the moment here. And how about the shear? Second one, if the beam is short, this is the long beam. For the short beam, you do the same thing. We can see the crack occur here. Okay, the crack occur here is due to the shear here. So in reality, the beam can be failed both by the maximum moment on the top picture, or maybe in the combination of the moment and shear in the second picture. And that's what is the evidence show us to understand the problem of the beam subjected to what's so-called the transverse shear. We call this type TP like this, like a transfer. And by doing this, we are not only interested in the sigma, we also interested in the tau. Okay, and this is the example asking you to determine. This is for the chapter 6. Okay, and then you also can design this beam based on how allowable. This is going to be chapter 7. And they may ask you only to determine the maximum shear stress. This is for the analysis. This is just for the analysis. This is for the design. This is for the analysis. Okay. The problem can be mixed, both the analysis and design together. And you also later to determine the distance between the wheel or the bolt that you use to build the beam. Analysis later. I won't make it much. You will get confused later. Coming to the short discussion on this, you know that the beam subjected to transverse load. Okay, is we have the maximum shear, we will have the maximum moment. Okay, we can analyze to determine the sigma max equal to m max times y max divided by I. Okay, we also can determine the tau max equal to v max times q max divided by IT. Okay, that's called analysis. That's called analysis. In the design, we will use this one, and most of the time, sigma equal to my over I. These are the dimension of the section. We may write it I over y equal to I over y equal to m divided by sigma allowed when this is the maximum. So this one usually called the S, called the section modulus. When we find the S for the steel section, you go to the steel table from the manufacturer of the steel section. You just pick one that has larger S. Okay, you can get pretty section very easy. That's for the steel side. Anyway, what we have is the deformation due to shear. If you have the rubber beam and you see on this size before the application of the shear is straight line, and when this one subjected to the V, let's say the V may be equal to 100 kilonewton. What we have is the deformation over here and over here is zero. That means it has the zero deformation on the top and the bottom. That means at this point the tau is zero. For the observation of the deformation of the rubber beam. Okay, and then the maximum deformation occur here. What is here? Here is the line that's passing through the centroid of the section. The deformation large. That means the stress is large. Okay, by doing this, if you draw this section with the rectangular section, the distribution of the shear gonna be zero here. Gonna be zero here. Since the deformation is the curve, okay, the distribution of the shear stress in this case is going to be something like this, okay, and the tau max going to occur here. This is important. Sigma max occur on the top or on the bottom or sometimes both. That's it for the chapter 6. Okay, sigma max on the top or on the bottom or both, depending on the section. Both for rectangular. Okay, bottom for the T. Remember, that's for the positive moment. But this time, the maximum occur at the axis that has the centroid. Okay. Usually, this point has zero normal stress from chapter 6. Okay. I got to write it again from the chapter 6. This is what? This is positive moment or negative moment. This bit. This one in tension. This one in compression. Right? This due to the negative moment. If this one is negative moment, this one gonna be in tension. The top gonna be in tension. This one gonna be in compression. This is the normal stress distribution for the rectangular. This is going to be the shear stress distribution for the rectangular. Again, if we change this one to the T section, just take this one to the T section. For the T section, like this. Okay, we have the normal axis here. For this one, what we have the distribution of the stress. Top is in tension. Okay, top in tension. Top is in tension. Bottom is in compression. This time the bottom is larger. Why? Because measured out, this is larger than measured up. Okay, and also this one, the distribution of the shear stress is zero and zero here. And we have the equation tau equal to VQ over I divided by T for this section. Okay, listen. On this point divided by the width, let's say this is 100 millimeter. On the bottom here, let's say is 10 millimeter. They are different, right? Different by what? Different by 10 times. When you divide this thing by 100, that is going to be small. When you divide this thing by 10, it's going to be large. Okay? By doing that, the normal stress of curve here, is going to be something like this. Very similar to this portion. But at this point, it's going to jump up 10 times larger. Okay? And then the author is going to have the shape something like this. It's going to be something. And then this one going to be how max. Remember everything. Remember this. Ajahn, how about this one? Okay, another classic one is the eye section. We use a lot of steel section in the building of the structure. This is double symmetry section. Okay, if this one is the eye, just put the eye over here. What so-called on the top is going to be in tension, right? This one is tension. On the bottom is going to be in compression, and then you got the triangle with the same shape. Ajahn, this one and this one is the same, right?
Yes, it's the same. Because both of them double symmetry. Both of them double symmetry. But the shear is different. The shear on the top is 0. Okay? The shear on the top is 0. On the bottom is 0. But the width here is 100. The width here, for example, is the 10. This is going to have the shapes of the shear stress distribution very low like this. And then you divide this one by 100, get this value. If you divide by 10, you're going to get this one bigger. And this one going to have something like this. And some people who have dark mind may think this is the shape of something. It's similar in the Indian culture. Okay. I want you guys to remember things. Ajahn, how about the C? The C and the T is the same thing. The C and the T is the same thing. Okay. It is in single symmetry. Okay. For the C, the top is going to be small. The bottom is going to be large. This is going to be in tension. This is going to be in compression. Okay. And then over here, due to the change in the width, the shape of this is going to be something like this. Remember, Ajahn, many times they ask you to draw the stress distribution, and there is a question in the midterm examination asking you to draw the stress distribution in one problem. Okay, so go back. Also take a look at chapter 1. Also take a look at chapter 5 to see the stress distribution. Okay, chapter 1 we have the tension and compression, and we have Flexure. Okay, and chapter 5 we have torsional shear. They are different from the Flexure. Okay, I remind you on this. And that is the thing that I like you to understand physically. Coming to the problem that show us the effect of the shear. Shear, like I said, shear. If the beam is subjected to this type of force, we will have the shear stress like this. We will have the moment like this. The shear is maximum at the end of the beam. Okay. Again,
How about this one? This one also. If you have this one, your shear diagram is going to be something like this. Your moment diagram is going to be something like this. This one also have the Vmax in the end of the beam. And then if your beam made by the wood, you will see the crack occur at the end of the beam. It's always like that. And then how come crack is in the horizontal direction when you cut the section? Okay, something like this. The small piece of this has the maximum stress at the middle. Okay, so the crack always occur at the middle, and this one is the wood, right? When is the wood? In the wood, we will have the grain, the grain in this direction, and then the state element of this is going to be something like this. This one cannot cut across the grain of the wood. The crack is due to this one. So when the crack due to this one, the crack always in the longitudinal direction of the beam. Okay, that's explain. And then in case of confused, we will have the lab, the method testing lab to show you about it. And one thing I like to remind you, one, the maximum shear stress occur at the middle, okay, at the middle height of the section. Second, maximum shear occur at the end of the beam. So we will see the crack at the middle and at the end of the beam. Why is crack in the horizontal? Because in the wood, okay, the woods have the grain. It cannot cross the grain. You can cut it in the direction of the grain because it's weak. Okay, that's extending in the physical meaning. In the future, I think rich people start to build the wood beam 100 years ago, like my home, built by golden tech. Okay, my home. Some people still in Cambodia. The golden tech still rich over there. You can import into Thailand because it's very expensive. Yeah. Poor people live in the timber house. Rich people live in the concrete house. Okay, nowadays, think of it. Poor people live in the concrete house. Rich people live in that expensive wood house. Okay, and new business will come later. Okay, let's see. This is what I'm saying to you. For the rectangular, the maximum occur here, and I should say that the maximum here is the tau max equal to 1.5 Vmax divided by A. I like you guys to remember this one because we will use a lot in the design of the beam. Okay, and this is what I said is the crack at the end of the beam, and I explained to you already. And what I mentioned about the golden tech here, you know, wood need times to go up, especially the wood one. Some of my house wood big like this. That is like a 50 years old tree before my grandfather cut it. Okay, and would we do some kind of commercial forest? We do the commercial forest. We may plant the golden tech, but instead of taking 50 years, we may take 10 years. We may get a small tree. So for the small tree, we can cut for the small section. But for the small section, we can combine them together by gluing them. In America, we call this thing as the cool lamp or cool lump. Okay, it is come from the glue, lumber. Lumber is a friend of timber. Lumber is a tank mine, okay? The tank mine, okay? And then you can glue together. And this is going to what? You can spend small time with a good, what's so-called wood cutting process and good manufacturing process to stick it together with a very good glue. Okay, so you can build a larger section of the wood by the small one. What's so called? If you want to glue it, this one will not work together. It can take very small force or small loading. If you stick them together, you're going to build a large wood section. This one is going to take a lot of loading. Okay, and I call some of you guys who may possess a good and large land do some kind of commercial forest. This kind of business is kind of popular in the Norwegian region, in the Scandinavia. They plant a lot of forests and use them. Engineering use them. Engineering use them like this one. And in Thailand, one of your senior, he graduated about 20 years ago. He had this type of business in Surat Thani also. Yeah, he worked with the Palawu, Mayang Pala, and then do some kind of engineering stuff and sell it for the luxury furniture. Okay, send to them some kind of furniture company. Anyway, let me go further. This is for the reinforcement. Okay, we're going to have this kind of stuff, this kind of thing to taking care of the shear stress transferring. And this is the equation, how equal to VQ over IT. V is the shear, I is moment of the shear, T is the thickness. The Q is the hardest part. Okay, is the moment of the area above, below the point you're looking for the top. With respect to the north x, I will show you later. Okay, and then what I have is this equation, how max for the rectangular section, and also how max for this section is going to be calculated from V. Actually, is for the V max. This one is the area of the web. Okay, area web. That's thinking about the left portion of the section, divide the V max, as is going to produce the top max. We're going to use this one in the design of the section. And for the rectangular, this one going to be 4/3 V max. Let's say supposed to be V max over here. Rectangular 1.5. Circular 4/3, 1.333. Okay. The I divided by area of the web. How about the T? No, the T you got to use the original equation to determine the top max of the T. Okay, and this is I should break it for 5 minutes, and we will come back. Spend like 25 minutes to finish this problem. Okay,